Good evening and welcome to Astronomy at the Virtual Beach. My name is Samer Hariri. I'll be your host, your lunar host for tonight. I'm an instructor of geology and astronomy and a co-founding member of the Farmington Community Stargazers. Tonight we're going to feature the moon for you, and we got the telescope set on it already and ready to go. I'll give you a little bit about the moon. We'll talk a little bit about some of its parameters before we showcase the live views here. Hopefully I'm getting through voice and video. If the sound is not good or if it's not loud enough, please do let me know. I can fix that, but there's a delay. So I'll be looking at the chat to see if there are any questions. And Carrie says that you're not hearing me well. If that's the case, I can drop the music sound a little bit more. How's that? Am I getting across okay to everybody? It seems like it's good. All right, excellent. So, welcome to our little lunar show here. And to start things off, let's talk a little bit about the moon in our sky. Here's a photograph that I've taken toward the end of summer there in August, late August, over Lake Huron. And there's the moon rising in the east over Lake Huron. In our sky, the moon's disk looks about the same size as the sun in our sky as well. A coincidence that allows for certain astronomical things to happen the way it does in terms of solar eclipses and whatnot. But in a camera like this, in a regular DSLR where you want to get the stars in the background, you take a long exposure and that washes out the light from the moon because the surface of the moon is reflecting a lot of sunlight back to Earth, so it's a pretty bright object in our sky. We can zoom in on the moon, and when we do, we get a better image here that showcases the features on its surface. So here we see a 180 millimeter shot with the DSLR over Lake Huron, and there's the moonrise. There's a boat right there sailing in the distance. In this phase of the moon, it's already past full, so we're seeing the waning gibbous, and the terminator of the moon is the side where you don't see that perfect circle, so to speak. That's the side in this case where the sun is setting on the moon. The other side, that's somewhat a semicircle there, we call that the Lunar Limb, the Lunar Limb. But from this image you can see, first of all, the color looks kind of orangish because it's an atmospheric effect. The red portion of the spectrum is being dispersed, so we see more of that orangish reddish color as the moon rises. But you can see that there are features on there that are quite visible, and we'll get to talk about those features tonight. Through a telescope, the moon looks a lot bigger with some more details showing. Here's an image that I took, I think back in May or June, whichever day that we had that lousy penumbral lunar eclipse that wasn't really visible with the eye. You had to really take image comparisons to see it happen. But there's the full moon from not too long ago, and on the full moon you are able to see these darker regions. We describe these as Themarias, or they translate to seas. Back a long time ago, before we looked at the moon through telescopes, people used to think that these dark areas on the moon were seas and oceans. But we know that's not the case. The moon does not have an atmosphere, and there's no liquid water on it. You see a lot of the craters, and the craters have what we call ejectas, these lunar dust and meteorite dust that just flies away from the place of impact, and it can land several thousand miles away from the lunar from the impact site. And on a good night through binoculars, you can see the Tycho crater and the ejecta from the Tycho crater. The neat thing about this is when you look at the limb, it is not a perfect orb. There are mountains there on the horizon in the distance. You can see more of them down here. The lunar surface is filled with craters and mountains, and we'll showcase that tonight. The Earth-Moon distance can be given by this image here taken by OSIRIS-REx, the spacecraft that's going to one of the, I think it's a comet or an asteroid. Can't remember which one, but one of the two. And this image is from 3 million kilometers away. So 3 million kilometers away, you look back at the Earth-Moon system and you see our little tiny satellite orbiting the Earth. That distance is about 240,000 miles on average. It's closer sometimes it's farther away. And when the moon is closer and it's a full phase, they call it the super full moon or whatever. But it's very difficult to visually see that without taking images of both full moons and compare them. But 240,000 miles, believe it or not, my car has that many miles. As a matter of fact, it's close to 250 by now. So some of us have driven that far. It's taken us 20 years, but nonetheless, there you have it. The diameter of the moon is about 2,160 miles across. So 2,160 miles. If you're driving at 70 miles an hour from one edge of the moon to the other, that's about a 30-hour trip if you don't make any stops. So you can drive across the lunar surface, so half a hemisphere, in about 30 hours nonstop. And of course, the other 30 hours on the other side. So you can go around the moon in 60 hours if you don't stop. Now, of course, you can go faster if you're flying, but we're assuming you're on a lunar rover that can go 70 miles an hour. Here is a selfie of us yesterday. This was taken on September 24 from a satellite whose sole purpose is to image the Earth and monitor any of the atmospheric changes that it has and any of the land feature changes that it has. So almost on a daily basis, this satellite takes an image of Earth. So there we have the Earth yesterday. And I think based on the location of the continents here, noon would be almost in the middle. So this is in the morning time, maybe like 10 o'clock, 11 o'clock in the morning. So think about what you were doing yesterday at that time, because that's the selfie, right? That's the selfie that was taken yesterday. So imagine what you were doing. And here we are being viewed from 1 million miles away. So this is about 1 million miles away from Earth. Zoomed in this case, and cropped. But yeah. So what is the moon compared to the Earth in terms of size? That's the size to scale. So it's a pretty small object. Takes about almost a little bit more than 3.5 moons to cover the entire disk of Earth, if we're just considering the two-dimensional circle here. I can show you that. Looks something like that. So not quite 4 full moons, but almost 3.67, or some number like that, some ratio like that. At about 2,160 miles across, It's almost the width of the continental United States, a little bit less if you start one edge of the moon way up there where Maine is. You won't quite get to the California coast there, or the Pacific coast there. Almost. So, with that said, I think maybe we should start looking at the moon. So let's open up our camera software here. This is Digicam Pro. It's a free software available to control DSLR cameras, and that's what we're using tonight. I have my DSLR camera attached to a refracting telescope, and this is what the moon looks like live and raw through that camera. What we can do then is play around with the settings here and decrease the exposure. So let's control the camera's exposure here. And because the moon is so bright, we can decrease that exposure and bring out more of its feature without trying to lose a lot of the other side there. So let's increase that to -1. And that's a little bit too much. Just got to find the right balance there. Maybe 1.3, maybe 1.7. There we go. We can zoom in. So there's our live image of the moon. I'm not sure how good the quality is that's streaming, but you could see that there's a waviness. There's some kind of a wavy thing happening in the live view here. That is the turbulence in the upper atmosphere. Now that the sun has set, Earth is radiating heat in the form of infrared radiation. So infrared electromagnetic waves are being radiated out into space as the Earth cools down. And you see lots of that turbulence. We call that the seeing in astronomy. And it's not too bad tonight. And sometimes it's a lot more, other times it's a lot better. But if we zoom in further, I don't know if we can do that. Oh, we sure can. You can see that waviness. Actually, it's pretty bad. So, and that's expected. We are in the fall after all, and the temperature changes dramatically once the sun sets. But there you have it. The side that's in the shade here, where you have the line between the shade and the light, we call that the terminator. And then the other side where you see the semicircle there, that's the lunar limb. At the terminator, right now, given the phase of the moon, this is a waxing gibbous. The moon is on its way to becoming full. It takes about half a month to do that, about 2 weeks to do that. So in a few days, it's going to be full. So that means this terminator line is going to migrate towards the left side of the moon. Therefore, what you're looking at there is the boundary between night and day. The boundary between night and day. That means it's sunrise. If you're standing there, the sun is rising, but it's a very slow rise. Every day, a little bit more of that shade is lit by the sun, because the moon rotates around its own axis almost in sync with the amount of time it takes to go around the Earth once. It's tidally locked, so we always see the same side of the moon, give or take a little bit from the edges, because the moon will not quite wobble, but sometimes we will see more of one side, sometimes we see more of the other side. We call that libration. So lunar libration is why we get to see a little bit of one side and a little bit of the other side as the moon goes around the Earth. But for the most part, the same side of the moon always faces us because the moon is tidally locked. So we never get to see the far side of the moon. We only see the near side of the moon. To see the far side, you have to go up in a spaceship and orbit the moon and check it out from the other side. And we've seen that. We've imaged the moon, and the other side, the far side, looks very different. It doesn't have a lot of these darker regions that we call Themarias. The common misconception about the moon here is that the other side is the dark side, and that's not true. The other side could be completely lit when we have a new phase, when we don't see the moon in the sky, when it's a new phase. That means the other side of the moon is completely lit by the sun. So the dark side of the moon today is the side right here that is in the shade. We can't see that. But at any given point in time, half the hemisphere of the moon will always be lit by the sun. And we're not seeing the other side of the moon that's lit here. Let's take a preview, and when we take a preview, what happens is some of that turbulence in the atmosphere disappears, and we get a nice sharp image of the moon here. So let's do an exposure of, I'm just guessing here for now, 1/125 seconds, and let's see if that gives us a nice photo. That's not bad at all. So now here's a photo of the moon that we can play around with a little bit. You see these darker regions. Those are called Themarias again. Themarias happened because a long time ago when the moon was forming, it was being heavily bombarded by asteroids and meteors. So these impacts were so powerful that lava would ooze out from beneath the surface and would flow on the surface and cover any craters that existed beforehand. And then when it solidified, it turned into that darker material. On Earth, when lava cools, it forms basalt if it's closer to the oceanic crust. So if it's made of oceanic crust, if that magma is made of oceanic crust, then it becomes basalt. So that's what we're looking at there, is the lunar basalts in those Themarias, in those seas, quote unquote. We give these seas names. This is the Sea of Crises, I think. This is the Sea of Fertility. This is the Sea of Tranquility. And this is the Sea of Serenity. So, crises, fertility, tranquility, and serenity. Those are the names of these features. This big one right here, which half of it is in the shadow area, is called Imbrium, which means the seas of rain. The Apollo 11 mission landed somewhere in this region right there, in Tranquility Base. So somewhere in this region of the moon, you have the lunar lander, or part of the lunar lander, and then all the tracks of the lunar rover, all the footprints of the astronauts, and then the flag. And no, you can't see any of those with binoculars or a telescope from Earth. You can get to see them from lunar orbiters that take images of the lunar surface, but not from Earth with those kinds of telescopes. Now, some people have good imaginations. They can say, oh yeah, that's the shadow of the flag, but highly doubtful given how small those objects are compared to the size of the moon. But right there, where the mouse is, in 1969, that's where we landed, that spot right there. And we always get to see that spot because that side of the moon always faces us. The Themarias, these basalt flow regions, they are about 3.5 billion years old. So 3.5 billion years old, that's when they happened. That's when they seized, actually, and all those lavas became solidified into those basalts. The other features of the moon that are not Themarias, we call those Lunar Highlands. Lunar Highlands. And the Lunar Highlands are older. They formed very early on when the moon crusted from its formation. And we'll talk a little bit about that formation here in a few minutes. But the highlands are are between 4.1 and 4.4 billion years old. That's how old those rocks are. And they're not basaltic rocks. There are rocks that are more rich in silica. They don't have a lot of iron in them, whereas basalt has some iron in it. And these are the silicate rocks that formed when the moon pretty much was completely molten, and the silica-rich materials rose to the surface via a process we call differentiation and formed those silicate-rich rocks. A mineral they contain is called anorthosite. It's a calcium-rich plagioclase, for those of you that are geologists out there. And when we returned some of those samples, we were astonished to see how similar those rocks are to the rocks that we have here on Earth. I have a couple rocks here, not from the moon, sadly, but they represent the analogs of what those lunar rocks would look like. So let me open up my document camera here. And we'll show you what the rocks look like. And it seems like I'm having some issues. All right, while I deal with these issues, we can talk a little bit more about the age of these rocks. So they say that the moon formed after the Earth formed. So the Earth formed at about 4.543 billion years ago. And just recently, in July, they published a paper that showcases the moon forming about 140 million years after the Earth formed. So the moon formed 140 million years after the Earth formed from a collision between a Mars-sized object and Earth. During that time, Earth was semi-molten, so the entire planet was in a state where differentiation was taking place, the mantle was quite in the molten stage, and it was actually forming as that Mars-sized object collided with Earth. So parts of that Earth then was sprung out into space as debris, cooled, and then reassembled as the moon, and that's why it's tidally locked to us the way it is. But that's also why all the rocks on the moon's surface are very similar to rocks on Earth's surface. So that's quite a peculiar thing. They say that the moon hardened in its form after that formation took place around the same time when Earth's core pretty much settled in. And that took place about 4.4 billion years ago. 400 million years later, there was a period of heavy cratering and heavy impact rates. So leftover debris from the formation of the solar system was pretty much bombarding the moon's surface, Earth's surface, Mars, Venus, and even Mercury. But we don't get to see a lot of craters on Earth as much as we do on Mars. As much as we do on the moon. And that has to do, of course, with Earth being, first of all, Earth having an atmosphere. Second of all, Earth being geologically active. We have tectonic activity on this planet. And we also have surface activity such as weathering and erosion that could pretty much bury craters and just wipe them away by subducting lithospheres and things like that. So We recycle the surface of Earth and get rid of all the crater evidence, but yet we still see some of those craters hanging around today, like the Barringer crater in Arizona. That one is about 50,000 years old, if I'm not mistaken. And it's still there because it's been surviving some of these processes. All right, so I'm gonna switch over to my document camera, and I'm gonna show you two rocks. So let's see here. This is the first. Were you able to see that? Or is it not switching screens? There we go, yeah. So that is what basalt looks like. And really that's what some of the lunar basalt looks like. Of course, this is from Earth. We call this river basalt. And you see a lot of holes in it. Those are the air bubbles escaping as the lava is cooling. So then it retains the shape where those air bubbles occupied. Of course, on the moon, you won't see them as nicely eroded and rounded. That's what happens here on Earth. But a lot of the rocks brought back from the Apollo missions showcase lunar basalts that almost look like this. So these are the rocks you expect to find in the Themarias, so in the darker regions here of the moon. In comparison, I don't have with me the anorthosite, but I have a similar rock here. So this could be contruded as the anorthosite of the Highlands. That's what it would sort of look like. So a little bit of geology there. All right. Let's go ahead and take another shot of the moon here. And what we'll do is I'm going to reduce the exposure. So maybe 1/200. And I'll do a capture this time because it will be a higher resolution image than just a preview. Now the question is, where did it go? Ah, there we go. So let's open it up and let's zoom in. There are mountains on the moon. These mountains are formed from ancient craters. They don't form because of tectonic activity like the mountains that form on Earth. They form from crater impacts, right? So when an impact happens, we get the crater rim, and over time, that crater rim pretty much gets buried under layers and layers of regolith, lunar soil, or lunar sediment that lands on it from ejecta. So as more asteroids collide with the surface of the moon, more of that lunar regolith encompasses the entire surface of the moon over time. So then you get these gently sloped mountains that could be quite high. These mountains can reach higher than Mount Everest by at least 2 kilometers, some of them. But they're gently sloped mountains, meaning that it's not a lot of effort to climb one of these. It just takes time. But again, these mountains formed because of ancient cratering that took place, and then of course the lava here filled in some of that crater that used to be there. Now you can notice here that some of the craters that are in Mare Imbrium there, these craters happened after the lava flows. So what a lot of these planetary scientists do is they can relatively date the ages of some of these craters and when they happened, because you can look at something like this and now you can play crater detective by thinking, okay, what came first, this feature or the feature that's inside of it, right? Similarly, when you look at the ejecta here, right? You notice that the ejecta happened after all these other features on the moon. So therefore you can date the source of that ejecta given what features it covers on the moon. When we look closely at the terminator, you can see that there are areas lit, and then you have darkness. Those are really tall areas that are elevated quite high above the rest of the surface here. So what's happening there is that the sunlight is catching the peaks of those crater rims, and they appear to us. If you watch the moon throughout the course of the entire night, so if we had more time here to compare what the moon will look like in 6 hours, we will see more and more of these shadowed areas as the sun rises on that horizon. You can see more of it here, and this is a very nice example. Notice that crater rim is lit by the sun, and it extends out beyond where that shadow is. Let's go back to the live view. And what I would like to do is actually zoom in. Notice how in the southern part of the moon, it's heavily cratered. Not a lot of basalt flows happened in the past in that region. So a lot of these craters took place during the late heavy bombardment about 3.9 billion years ago. And we see a lot of those surface features there as a result of that heavy bombardment that took place. Now, I'm not very versed on the name of the craters, so you'll have to forgive me for not knowing some of these names, but I should. I know one of them here is Plato. I don't know which one. One of them is also Copernicus. Let's zoom out here. Can I figure out which one's Copernicus? Maybe it's that one. Maybe that's Copernicus. And then Tycho. Is Tycho visible tonight? I think so, yeah. I think Tycho is somewhere in this region here. So how hot does it get on the surface of the moon? Well, that depends. If you're on the side that's lit by the sun, the temperature can get up to 120 degrees Celsius. So that's way above the boiling point of water. So that's about 250 degrees Fahrenheit. So why is it that way? Well, the moon has no atmosphere. Whatever little atmosphere it has is pretty much made of lunar regolith, little tiny, very tiny light dust particles, and they're very temporary. This is the reason why all the footprints that we left on the moon will remain there for a very long time. The only way they can get disrupted is if some impact happens and then they get covered by more lunar dust. So the only type of weathering and erosion, quote unquote, that happens on the moon is impact-based weathering and erosion, not atmospheric-based. So no winds other than solar winds, no water, no rivers to flow and create features and remove features. Now, there is some ice here and there near the poles of the moon. But are these ice enough to create any sort of glaciation? We don't think so, but with planetary geology, you never know. You have to open up your mind to such things happening on other worlds. The dark side or the night side of the moon, can get pretty chilly, negative 280 degrees Fahrenheit at night. That's about negative 170 Celsius. So in the night side, it's way below freezing. On the day side, it's well above the boiling point of water. And the astronauts had to endure that temperature, but of course they were wearing pressurized suits that were protecting them from all those extreme temperatures. No atmosphere on the moon also means no sound. Sound cannot happen because there's nothing for those sound waves to travel through. No medium for those sound waves to travel through. All right. I'm going to go through the chat here to see if there are any questions. And if you have any questions at this point, this would be a good time for me to answer them before we move on with our agenda here. All right, so it looks like Robbie has a question there. At roughly what spot was the first millennium? We answered that, yep. So yeah, that landing site, you cannot see that from telescopes here on Earth. You have to be orbiting the moon to get a glimpse of those little tiny shadows. All right. Let's see here. One of the things that can happen on the moon is new rocks can form, and this has already happened, that's why I'm discussing it. New rocks can form that are not basalts or anorthosites. Those rocks can occur from impacts. When an asteroid collides with the surface of the moon, that energy is enough to create some melting. So there's some melting that takes place, some metamorphism that takes place. And you have all these pieces, all these chunks of rocks flying out from where the crater source is. Some of them that are beneath where the impact site is get integrated into some of that temporary lava that forms during a big impact. So this has to be a very energetic impact. And those particles, those debris, pretty much then get integrated into a new rock that we call lunar breccia. Lunar breccia. And when that happens, they look similar to rocks on Earth that are sedimentary in nature that we call breccia as well. It's just that the process is completely different. On Earth, of course, breccia form when sediments cement around chunks and pieces of other rocks that are not quite as eroded. But on the lunar surface, those happen from impacts. So impact structures can create new types of rocks, and we've seen some of those returned as well from the Apollo missions too. All right. Derek is asking, if there was no sound waves due to the atmosphere, how did the astronauts communicate? Radio. So they had little microphones in their helmets, and they were completely isolated from the lack of atmosphere on the moon. So their pressure suits pretty much were a completely isolated system. So they were just communicating through radio. Yeah. Okay. Let's see here. I think we can take another capture here, but this time what we're going to do is we're going to show you the other side of the moon that is not lit. We're going to show you the dark side of the moon. So we're going to take a long exposure. This long exposure is going to... I'm going the wrong way. This long exposure is going to pretty much wash out all the details on the lit side, and it's going to show us the dark side of the moon. So let's see if 2 seconds is enough for that. Not quite, but you can kind of see a faint light there. Let's try again. Maybe we'll do 10 seconds this time. Ah, there we go. And now we're seeing some stars. So we've completely washed out the lit side of the moon, and that has revealed the night side. And what I love about doing long exposures like this of the moon is you see these bright dots at the terminator. Those are the peaks of those crater rims and mountains that are catching the sunlight just right. And you can actually see Tycho's crater there. Half of it is on the lit side, half of it is not. But the rim, the western rim of the Tycho crater is catching the sunlight because it's high enough above the lunar surface to do that. But the rest of it is in the darkness. And you can see a lot of those peaks there. But you can also see the rest of the moon, and we can do better. Let's do a 30-second exposure. And while it does that, I'll let you ponder some of these here. Notice that there are some stars now in the background, but that's all going to be washed out because we're increasing the exposure. And tough to see much more. You can see more of the surface features on the lit side here, on the dark side, when the moon is a crescent. Not much when it's a gibbous. And that's because it's just too much glow. So perhaps a shorter exposure will do the trick. Now, the reason why we get to see some of that sometimes is due to what we call earth shine. So just as the moon is reflecting light and we can see it from Earth, the Earth is also reflecting light, and that light then reflects off of the surface of the moon and comes back to us. It's just a lot dimmer. So we need a very long exposure to get to see it. And there you see some of those brighter regions. Those are some of the craters. And then the darker stuff, that's part of the Themarias. I think that's Grimaldi or something like that. It's a crater. But that's Earthshine. That light that you see there on the night side of the moon is from the Earth. And here's something interesting as well. Right now, we see a waxing gibbous phase. So we see this much of the moon lit up. If you were standing on the moon, looking at Earth right now, you would see Earth as a crescent that's waning, that's becoming thinner and thinner and thinner. So, fun fact, the phase of Earth on the moon is opposite to the phase of the moon that we see from Earth. And that kind of makes sense because now you're looking at things from the opposite angle. So on the day that the astronauts walked on the moon, I believe the moon was like this, if I'm not mistaken. Someone can look that up for me, but I think the phase of the moon was a waxing gibbous in July 1969 when the astronauts landed on it. So Or maybe it was a crescent and they saw the gibbous Earth. Maybe that's what it was. Either way, fun fact. Looks like we're losing it a little bit there. Not perfectly aligned tonight, but good enough for that 1 hour. At some point, it's going to pass the meridian and the telescope's going to have to flip around, but I think that's not going to happen before 9:30, so we're good. All right, one thing that can happen with the moon that is quite difficult for a lot of people to consider is this idea that large impacts that strike the surface of the moon can eject material from the moon out into space. The amount of energy that some rocks, some debris that can fly off the surface of the moon is enough for them to escape the moon's gravity. And now they're just out in space floating around. So during the late heavy bombardment, when all these craters happened down here, so much lunar rocks were ejected out into space. And they were forming as the impact was happening, meaning that the impact was melting and creating some metamorphic processes to form those lunar breccias. And eventually those lunar breccias were just floating around in space. And every now and then, some of them will get to fall down to Earth. And those are what we call lunar meteorites. Those are the lunar meteorites. Earlier I was watching one of our founding members, Jesse Mason's presentation on the extinction of the dinosaurs. And someone brought up the idea that rocks could fly up into space. And of course, if that can happen, if a large impact can hit the surface of the Earth, and now you have rocks flying out into space from Earth, those rocks could end up on the surface of the moon. And just like we can have lunar meteorites on Earth, there could be meteorites that have Earth origin on the lunar surface. So I guess you can call them Terran meteorites. Similarly, we can have meteorites that come from Mars because some large impactor hits the surface of Mars, ejecting rocks into space from Mars. Those rocks can eventually find their way to Earth and some other planets as well. And that's how we can have Martian meteorites. And how do we know these things? Well, to know whether or not a piece of rock came from the moon or came from Mars, you really have to know the rocks of Earth. And if it has nothing that closely resembles the rocks on Earth, and of course we do studies of isotopic ratios and things like that, then you know its source is extraterrestrial. So whether it contains mineralogy that's foreign to what we know here on Earth, or isotopic ratios in those minerals that are not in line with the isotopic ratios that we have here on Earth, then you know its source is extraterrestrial, meaning from another body. So the moon was a waxing crescent on July 20th, 1969. That's why they saw the Earth as a gibbous when they were orbiting it, and you had that Earthrise as they were orbiting. That phase of Earth was a waxing gibbous. It's the opposite. So, the moon has fascinated people for a very long time. It's one of these things in the night sky that when I was a kid, I remember maybe 7, 8 years old, my parents would be driving at night, and I'd look out the window of the car, and I would see the moon in the sky. And no matter how far we went, the moon was always in the same place, meaning that it was kind of like following us. It wasn't just lagging behind with the buildings and the trees and things like that. And from that young age, I've always pondered, why is the moon following me? Why is the moon always trying to follow us? And of course, that has to do with its size and distance, right? You don't see that relative motion because of how far away it is from us. But the moon is also a fascinating object that has inspired serenity, romance, you name it, poets. It's always been an object of fascination in religion, so on and so forth. So in the, and I'm going to get this wrong because I don't quite remember, this episode was a long time ago, but in the famous words of Philip J. Fry from Futurama, he says, the moon is this mysterious, beautiful, romantic thing hanging all the way up there in the sky where I can't reach it no matter how much I wanted to. And I've always found that to be quite the impactful quote from an animated TV show. But nonetheless, I feel like there's so much truth to that, and only a few people, only a few humans were able to set foot on a foreign surface like that. The only other planetary body that we've set foot on is the moon. And to think about that it's quite lonely to not be able to do that. It's quite sad to not be able to do that. I think most people have, at some point in their life, dreamed about setting foot on the moon. Perhaps. But if you can't go to the moon, you can wait for the moon to come to you. Here I have a little piece of the moon's surface. My only regret, of course, is that I can't share this with you physically, but at least I can show you. This is a lunar meteorite. That's a lunar meteorite. It's a breccia. Nothing on Earth has the isotopic ratios of what's in this rock here. It's got some feldspars in it, and it formed because of an impact. So there was a little bit of melting that took place, and this recrystallization and lithification, so there was some kind of a pressurized event that allowed for those little white pieces there to cement together in a sense, except the cementing agent here is caused by the impact. So that's a lunar breccia. That's what we're looking at there. I'm touching a piece of the moon. So like I said, if you can't go to the moon, sometimes your best bet is to just let the moon come to you. All right. If there are any questions, I'll entertain them. Otherwise, that is all I have for you tonight. Thank you for being here, and I'll go ahead and answer any questions that you have. And while we're at it, we'll take a capture. And there it is. That's a beautiful picture. All right, how did the moon rock feel? It was out of this world. That's the best way I can describe it. Would there be shocked quartz in there? I'm not sure of how much quartz there is on the moon, to be honest with you. From the rocks that we got back from the Apollo missions, most of it has plagioclase feldspars. That's the anorthosite, and then the basalts. So I'm not quite confident on how much quartz there is on the moon. There's lots of quartz here on Earth, but there are more feldspars on Earth's continental crust than there are quartz. But yeah, that's a good question. I'll have to look that one up. How did I come across the lunar rock? eBay. That's where I got it from. And it wasn't that expensive. You can find them sometimes when no one else bids. Some say civilizations destroy themselves before entering space exploration, and that is why we haven't found them still. I think... Yeah, we have quite some limitations, but I think our limitations are more political than they are scientific. And point in case is the 60s and 70s. We were able to go to the moon within months of, demanding that we should, So where there's a will, there's a way. It's just that today politics and economics gets in the way, and it's only because we allow it to get in the way. That's my opinion about it. All right, any other questions before we conclude the night here? What would happen to water on the moon? Would it evaporate? I think before it evaporates, it solidifies into ice because there's no atmosphere, there's no pressure. So that low pressure pretty much allows for water to be completely solid. But I think there is a little bit of sublimation that happens on the moon where the ice turns into vapor. But that returns quickly once you're on the night side, where the temperature drops immensely. So perhaps what happens is when you get to the day side, some of that ice sublimates into vapor, forming a very temporary, thin layer of water vapor above that area, but then it falls back down at nighttime as ice. So it's not a boring piece of rock. There is some activity. You just have to be creative and open-minded when it comes to some of the physical and geological things that could happen on the surface. All right. Well, thank you very much, everybody, for being here. Carrie, Elise, Derek, and all the rest. Rob, good to see you, Rob. Glad you came back. Jessica, thank you. And if I missed anyone else, my apologies. I'll go through the chat again once we're done tonight. But yeah, for all my students, thanks for being here. And then for everybody else, I hope you enjoyed this. Please go back to the GLAC website. Check out some of the other live events that are happening now. I think we have some live views that are going to happen from New Mexico. Deep sky objects. There's more than just the moon out there. There's Jupiter and Saturn and all sorts of other galaxies and nebulae out there that are going to be shared with you by some of our other astronomers in the region and in New Mexico as well. So enjoy the night, and until next time, take care.